All right, for 7, evaluating this one, I can already kind of tell that by plugging in 3, that's going to be a problem. If I plug in 3 here, that becomes 0. If I plug in 3 here, that becomes 27. This also becomes 27, so that also becomes 0. And so we're going to evaluate this by manipulating first. Try to do some factoring. I get x minus 3 over x, and then x squared minus 9, which is a difference of squares factoring pattern. So that becomes x times by x minus 3 times by x plus 3. So those would cancel. So let's now evaluate the limit as x approaches 3 of 1 over x times by x plus 3. And now I can plug in 3, so that would be equal to 1 over 3 times by 6, which becomes 1 over 18. So that becomes B. Okay, oof. Alright, was not expecting this one right here, but I do know how to solve this. This one is kind of a complicated one to explain. I'll do my best, but one thing that, here, I already have it planned out right here. One thing that a lot of students kind of forget about absolute value functions is the fact that they can be rewritten as piecewise functions. So I have that here. So I have right here x, well, let's actually start with the absolute value of x. So the absolute value of x can be written as a piecewise function of two different functions: negative x if x is less than 0, and positive x if x is greater than 0. So you combine those two for a piecewise function, and you get the absolute value of x. So same thing with x minus 1. You can see that you can think about it as negative x minus 1 with the parentheses, because that's just the same thing as negative x plus 1. And you can think about it as just x minus 1. So you can get those two functions and combine them into x minus 1. So I've kind of written them like so. So basically what I'm trying to say is that we already have a piecewise function, which is kind of weird, but this in and of itself can also be rewritten as a piecewise function, where I can split the x minus 1, the absolute value of x minus 1, into this piecewise right here, so long as I break it down by this domain right here. So with all that being said, we're trying to evaluate this limit right here as x approaches 1. But we're going to need to use a piecewise function to evaluate it from the left of 1 and to the right of 1. So we'll evaluate this expression to the left of 1, but we also need to take this x minus 1 right here and replace it with negative x plus 1. So taking this expression right here, I'm going to write it as x minus 1 squared, which is just x minus 1 times by x minus 1, and then x plus 1, over, now again, I'm interpreting this by using two different functions. The first one, from the left side, I'm going to use negative x plus 1. I'm actually just going to write it as negative and then x minus 1. They're the same thing. So this is the same thing as this right here, just you'd have to distribute that. And then, so let's do the limit as x approaches 1 from the left. I'll put this right here. Alright, well, I can see that I can remove this right here, which was the problem from the beginning, right? I can't plug in 1 right here, because then I get 0. But then the question becomes, well, how do I deal with the absolute value? Well, this is how you deal with the absolute value. So you have to evaluate it from the left and from the right side, and you also have to interpret the absolute value of x plus 1 from the left side of 1 and from the right side of 1. So we get rid of those factors right here. So then I get the limit as x approaches 1 from the left of x minus 1 times by x plus 1 over negative 1. So now let's go ahead and plug in 1, since I won't get an error for the, or a 0 in the denominator. If I plug in 1 here, I get 0, but I don't get 0 here. But altogether, I still get 0. So I'm going to get 0 over negative 1, which is just 0. Now let's verify that the limit from the right side is the same. So the limit as x approaches positive 1. So I have x minus 1, I have x minus 1, I have x plus 1. But now we're going to interpret this graph from the right side, which means I have to take this absolute value of x plus 1 from the right side, which would just be x minus 1. And we get the same thing where those cancel, although it's not going to be negative on the denominator. But I'll have the limit as x approaches 1 from the right, we'll have x minus 1, we'll have x plus 1, which is still going to result in 0. So because from the left side it's 0, from the right side it's 0, therefore the limit will be equal to 0. So I don't think you'll use that. If there is a question on the AP exam, it's going to be very rare. But still likely, I guess I should say. Alright, for 9, if f is the function defined here, then the limit as x approaches 1 of f of x is, so I can't plug in 1, because then I get 1 minus 1, which is 0. I also get 1 minus 1, which is 0 there too. We're going to use algebraic manipulation, except we can't factor, so we're going to use conjugates. So the conjugate to, this one's going to be conjugate. And the conjugate to our denominator is going to be square root of x plus 1. And I'm going to multiply the top and bottom by that right there. So let's say f of x is equal to x squared minus 1 over the square root of x minus 1. I'm going to multiply this by square root of x plus 1 and multiply the top by the square root of x plus 1. Let's see, I think I want to factor this right here. So that becomes x plus 1 and x minus 1. And then we added this factor right here, square root of x plus 1, all over. Now when I FOIL this part right here, I'm not going to FOIL these together because that would make it difficult, but this isn't bad. You always FOIL the conjugates part. So whenever you're doing these and you multiply by the conjugate, multiply the conjugates together. That's usually what helps you solve the problem. So square root of x times square root of x is x. Square root of x times 1 isn't going to matter because this is also the same thing, but it's negative. So those are going to cancel when you combine them. And then negative 1 times by 1 is going to be negative 1. So you can see how we ended up with common factors. So those cancel. So now I'm going to do the limit as x approaches 1 of x plus 1 times by the square root of x plus 1. And then now I can plug in 1. It won't be a problem anymore. That's going to be equal to 2 times by 2. So that's going to be equal to 4. Alright, for 10, let g and h be the functions defined by g of x is equal here. Oh, sorry, this right here. We have h of x. If f is a function that satisfies, so this is just saying that the function f is always going to be in between h and g on this interval right here. What is the limit as x approaches 1? Okay, so this is using the squeeze theorem. I can tell because it already gives us the condition of part of the squeeze theorem. We just have to verify what the limit as x approaches 1 for g and for h. And if they're the same, then that would mean that it have to be, f of x would have to also be equivalent. So I'm just going to plug in 1 for g of x. So g of 1 is equal to sine of pi over 2. And sine of pi over 2 is 1. Yeah. Okay, let's also do that for h of 1. So what's h of 1? So basically we're just evaluating the limit through substitution. So if I plug in 1 right here, I get negative 1/4, I get plus 3/4, plus 9/2. So then that's going to become, if I combine those two right there, that's going to become 2/4, so that becomes 1/2. 1/2 plus 1/2 plus 9/2, so that's going to be equal to 5, I think. Right? It's going to be equal to 5. Yeah. I think I did that right. Oh, wait a minute. I forgot this plus 4 right here. Hold on. I forgot that plus 4. Plus 4, so then that becomes 1 plus 4. That becomes equal to 5. There we go. So since they're both equal to 5, that would mean that the limit as x approaches 1 of f of x would also have to be equal to 5 because of this statement right here. So that would also have to be, yeah, that would have to be 5 right there. All right, for 11, I think we're doing something similar. Okay, so we have this statement right here where f is always in between g and h, or at least equal to. And then we're going to evaluate the limit as x approaches -1 for g and for h, and see if we come up with the same thing. And I'm going to evaluate just through substitution. So g of -1 is -1 squared minus 2 times -1 plus 3. So that's -1 plus 2 plus 3. So that should be equal to 4, I think, if I'm doing that right. And then h of -1, which would just be 1/2. If I plug in -1 there, that becomes +1, so that becomes 1/2. If I plug in -1 here, that just becomes -1 plus 13/2. So that becomes 7 minus 1, so that becomes equal to 6. So they are not equivalent to each other, if I did that correctly. So then in that case right here, it doesn't mean that the limit doesn't exist, but we do not have enough information. So the squeeze theorem can't prove whether or not, or can't prove the limit here. So pretty much we just don't have enough information. Okay, and that should be it for this homework.